Hello and welcome to this video lesson. In this video lesson, we will be looking at circuit analysis, and we're going to be doing two simpler circuits. In the first example here, we have a circuit which has a source, and this source provides power to resistors 1 and 2, which are currently connected in parallel. We know that the voltage drop across resistor 1 is 9 volts, and the current which is going through the resistor 1 is 2 amps. I'm going to start off by writing all the information that I have within my circuit. So here I have my V1, which is the potential difference across resistor 1, which is 9, and my current here is equal to 2. Whenever you have a circuit and you have two pieces of information on one resistor, you can find the other pieces of information using circuit equations. So let's do that first so we get all the information that we have on resistor 1, and afterwards we're going to go and find every other information. So at location 1, resistance 1 is equal to V1 over I1. We have those values, so we can just plug it in. So 9 over 2, and that's going to give us 4.5 amperes here, sorry, 4.5 ohms here, so I'm going to put 4.5 here, and that's my resistance. And for power 1, the equation is V1 times I1, and that's 9 times 2, which will give me 18 watts of power on resistance 1. Let's analyze the circuit a little bit. We know that when a charge comes here, it's going to have 0 volts of 0 potential. So I'm just going to put 0 potential here. And then it's going to gain some potential when it goes through the energy source here. So it's going to have some energy here, it's going to go here, and it's going to have some energy here. It's going to go either through this path and back to the battery to gain energy, or it's going to go through this path and come back and gain battery. So these are the two ways that 1 coulomb of charge can actually flow, or electrons can actually flow in. So I'm going to start by going through this path. If it goes through this path over here, it's going to lose 9 volts of, or 9 joules of energy. So every charge, or every 1 coulomb of charge, is going to lose 9 joules of energy, and it's going to come here and it's going to have 0 energy. So right here, we know that it's going to have 0 volts. And since it's losing 9 joules of energy here, since every 1 coulomb is going to lose 9 joules of energy here, then that means the voltage here has to be 9 volts. So if it's 9 volts here, that means if the charge was to go through this path, it will have to lose 9 volts here and it will have 0 volts here. And it also means that when it has 0 volts here, when it goes through the battery source here, it's going to gain 9 volts in order to have 9 volts here. So that gives us a lot of information about our circuit. It will tell us that the voltage drop here is 9 volts, and it will tell us that the EMF, or the energy coming from the source, for 1 coulomb of charge is also 9 joules, so that means the EMF is also 9 volts. I can put all those values in, so source has 9 volts, and location 2 also has 9 volts here. There was a piece of information that I had forgotten to put from this question initially, and the question itself does say that resistance 1 is equal to resistance 2. So resistor 1 and 2 are equal, so I can also add this piece of information here. I know that this is 4.5 volts, 4.5 ohms, and based on this I can find the current and the power. So to find the current, I2 is going to equal to V2 over R2, and that is 9 over 4.5, which will give me 2 amps here. So I can put that value in here. And I can find the power at point 2, which is I2 V2 or V2 I2. And that comes out to be 2 multiplied by 9, which gives me 18 watts of energy here as well. Now that I have this pieces of information, I can kind of figure out everything about the source, but there's one way of doing this is just to add up all the powers, and this will be the total power created by the energy source. But I'm going to do this differently. I'm going to use Kirchhoff's current law, which states that at any junction, the current coming into the junction is equal to the current flowing out of the junction. So I'm going to take this to be my junction 1. I'm going to call this I from the source. This is going to be I2, and this is going to be I1. And Kirchhoff's, and I'll just write here that at junction 1, current from the source is going to equal to the current 1 plus current 2. So current 1 is 2, current 2 is 2, and this is going to give me 4 amps, which is going to be the current which is flowing out of my energy source here, which is 4. And once I have this, I can find the total equivalent resistance for the circuit. So this is actually not the resistance inside of the battery. This is the equivalent resistance, and I want to make sure that you know that it's actually not the resistance inside the battery. That's a completely different way that we can calculate that, and we're going to assume that in this case that there's actually no internal resistance in the battery. But to find the equivalent resistance, all we have to do is to say that resistance from the source is equal to, or the equivalent, I'll just write equivalent here, is going to equal to V source over I source, which is going to equal to 9 over 4, which is going to be 2.25. And here I'm not looking at proper number of significant figures, so I'm just writing all the values in, but make sure that whenever you do get a question, you go back and check all the number of significant figures and to write your final answer in proper number of significant figures. The last step is to find the power coming from the source, and that's going to equal to the current from the source multiplied by the potential difference across the source, and that is 4 times 9, which is going to equal to 36. I'm going to put that final value here. And to check if your circuit is correct or not, or if your analysis is correct or not, always go and check to see if you add all the powers from the different resistors or loads, they should equal to the powers coming from the source. So in this case, I have 36, and that's equal to 18 plus 18, which means that my circuit or my analysis very likely is correct. On the second example here, I have a battery. This battery is connected to resistor 1 here, and that goes into this junction over here. That's split into 2 sections. One of them is going through resistor 2 and kind of stops here and goes back to resistor 4. So if we have a charge flowing or an electron, it will go through the power source, gain some energy. It's going to spend some of its energy here. It's going to go here. It's going to choose a path, either to go here or here. If it goes through here, it's going to spend some energy here and gain energy again. And if it goes through the other path, it's going to spend some of the energy here, some of the energy here, and some of the energy here. So for an electron, for sure it's going to lose energy in 3 spots, 1, 2, and 3, or 1, 2, and 3. I have a lot of information here, so I'm going to go and write them down. Energy, the EMF from the source is 80 volts. The potential difference across resistor 1 is 10, and across resistor 4 is 20. Resistance number 2 is 75, and resistor number 3 has a resistance of 150, and current going across resistor 4 is 1 amp. The first thing to do is look at the table, and in this case I have voltage and current here, so I can find the other two missing information. So let's do that first. For resistor number 4, resistance is going to equal to V4 over I4, and that's 20 over 1, which is 20. So I know that this resistance is 20, and power across resistor 4 is equal to the current multiplied by the voltage, and that is equal to 1 times 20, which is 20. So I'm going to put that information as well. Now I'm going to look at the circuit itself and find any information that I can. So if I have a charge or a certain amount of charge coming here, it's going to gain 80 joules of energy. If it's 1 coulomb of charge, it's going to get 80 joules of energy. So we're going to have a potential of 80 volts here. So I will write that here, 80. And then as we flow through the circuit, we're going to spend some of it here. We don't know exactly how much yet. We're going to have so much here. It's going to go either through here or here and spend the same amount of energy. It's going to have certain amount here. And it's going to come and it's going to spend 20 here. And it's going to have 0 just before it goes back to the battery. So I'm going to write that information here. Zero volts here. And if it's got 0 volts here, that means it has spent 20 volts here, or 20 joules for 1 coulomb. So it's going to have 20 volts here. Good, we know that much. However, we don't know how much energy is spent here or here, and that's what we're going to try to figure out. Let's talk about the current a little bit. So in terms of current, we have 1 amp, which means we have a lot of electrons actually flowing through the circuit here every second. That 1 amp is going to go here. It's still the same wire, so we're going to have 1 amps here. Still the same wire, so we're going to have 1 amp here. So I'm going to write that set of information. So current across 1 is equal to 1 amp, and I'll go and write that here as well. And we know that across the battery is the same, so I'll write that as well. Now this whole set of information has given me an opportunity to find the resistance and power here, and that's a good set of information. Also equivalent resistance and power here. So let's do that. Let's write everything that we know. Resistance 1 is going to equal to voltage 1 divided by current 1, and that's 10 divided by 1, which is 10. And power 1 is going to equal to I1 V1, which is 1 times 10, which is just 10. So this is ohms, this is watts, this is watts, this is ohm. So this is 10, and this is also 10. For the source, the equivalent resistance of the circuit is going to equal to the voltage across the source, or the potential difference, or the EMF across the source, divided by the current, and that's going to equal to 80 divided by 1, which means it's 80. For power of the source, that's going to equal to the current across the source multiplied by the potential difference, or the EMF. And here I'm using, note that I'm using epsilon here for EMF, but I'm using potential difference here. Just know that that's my convention when I'm solving things. It would be better if I just write EMF every time, but it doesn't make a huge difference in my calculations. I got 1 times 80, so I know that we got 80 watts of power in total. I had forgotten that we get the voltage here, so we can actually add a little bit more information here now. We have an electron that goes in, or 1 coulomb of charge is going to 80 joules of energy here. It's gonna have we're gonna have 80 volts here. There's a potential difference of 10 here, so there's gonna be a loss of 10. So from 80, we're gonna get 70 here. We can put that number in. And that's going to help us solve everything else because we know that when 1 coulomb of charge comes here, it has potential of 70. And when it goes here, it's going to lose 50 in order to get here with 20. So we know that the voltage across resistor 2 is going to equal to 50, which is the difference of 70 and 20. And it's the same potential difference here, 50, because if we got 1 coulomb of charge that comes here, it's going to lose 50 volts here to get 20, and if it chooses this path, there's only one resistor, so it's also going to lose 50 in order to have 20 here. So let's put all that information in, and we can solve for everything else now. To find the current across resistor 2, we're going to use V2 over R2, and for 3, V3 over R3. So we're going to have 50 over 75, and we are going to have 50 divided by 150. And we're going to have 1/3 here and 2/3 here. And we can just put those in. For 2, we got 2/3 and 1/3. I'm going to check and make sure everything works out here. 1 amp is coming up here. Electrons are going to choose to go with, try their best to go through the path of less resistance. We got 75 here and 150 here, so they're going most of them are going to go through here, and some of them are going to go here. So 2/3 here and 1/3 here. It makes sense. There's more going through here than here, and we got to make sure that based on Kirchhoff's law of currents, values also hold out. We got current coming in should equal to the current going out. We got 1 amp here, which is equal to 2/3 of amps plus 1/3 of amps, which works out perfectly. The thing that we need to do on our circuit is to find the power and just make sure all the powers add up. Power at point 2 is I2 V2, which is 2/3 times 50, and power 3 is going to equal to I3 V3, which is 1/3 of 50. This is going to give me 33.3 repeated, and this is going to give me 16.6 repeated. Put those values in. Again, I'm not looking for significant figures here. Power 2, 33.3, and this one 16.6. And I need to make sure, the best check to making sure that everything that you have done is correct is to add up all your powers from your loads and make sure that they are equal to the power from the source. And in this case, we got power 2 and 3, they add up to 50, this is 60, and this is 80. And this is equivalent to the power coming from the source, which makes sense. And this is one way to check to make sure that our powers are correct, and it helps us kind of get an idea on whether or not our circuit is correct or not.